Okay, so moving right along here in Chapter 8, we're going to talk a little bit more about solutions. In this particular section, we're going to look at solution concentration, which deals with the amount. So up until now, we've talked about what will make a solution, but now we're going to focus on how much solution we're dealing with, what amount of solute, what amount of solvent, all those questions I'm sure you've been asking yourself up until now. Well, finally, we'll be able to answer those. When we talk about concentration, a lot of times people just say concentrated solutions, right? That doesn't really mean a whole lot. Concentration is really an amount in solution. So when we talk about solution concentration, we're not going to be looking at dilute or concentrated things that may have, cut the mustard up until now. We're really going to be looking at specific amounts, and we'll see there's a number of different ways to represent solution concentration when we're dealing with amounts of solute per amount of solvent or per amount of solution. So there's more than one way to express solution concentration, but definitely a lot of ways far better than simply saying dilute or concentrated. So again, we've already defined this idea of amount of solute dissolved in a specific amount of solution. So there it is as a mathematical relationship: concentration equals amount of solute divided by amount of solution. Of course, that's a very generic way to represent the idea of solution concentration. So we have much more specific ways, and we have to be careful that we understand exactly which representation we're using at a given time, because they are different. They have their little spins, and each one's slightly different. So we have mass percent, which would be the mass of solute divided by either the mass of solution or the mass of the solvent, depending on which particular type we're talking about. There's volume percent, where instead of the masses, we're dealing with the volumes. There's mass per volume percent, which is actually fairly common, even though it seems a bit strange, but it's just a convenient way of expressing solution concentration. And then finally, the one that's most important to us as chemists is molarity, and that deals, instead of mass or volume, deals with moles, and that's what we as chemists tend to love, right? That's the unit that really tells us about how many atoms or molecules or ions we have. So molarity is the one we're going to use the most, but you will commonly see these other things, especially in the health professions. You'll see things like mass per volume percent with saline solution that is given intravenously in the hospital, for instance. So they're all important. We just tend to see molarity more in chemistry and some of the other ones more in other settings. Okay, so looking a little more detailed into mass percent. So mass percent is represented by lowercase m / lowercase m to indicate that we're dealing with masses of both the solute and solvent. And so that's the grams of solute and exactly 100 grams of solution. That's what makes it a percent, right, per 100. And of course, the solution mass is the mass of the solute and the mass of the solvent. That's the law of conservation of mass. We've been dealing with that since the very beginning of the course, and we've known about it for hundreds of years. Volumes do not conserve, so we have to be careful there. You can't just add volumes of solvent and volumes of solute when you're dealing with liquids, solutes dissolved in liquid solvents, but masses do add, and so therefore mass percent's nice and easy. I don't have to tell you the mass of the solution. If I give you the mass of the solute and the mass of the solvent, you can find the mass of solution. So either you're given the mass of the solution directly or indirectly by having the mass, or a way to find the mass of solute and solvent. Either way, you're able to find this mass percent, which is mass of solute divided by mass of solution. The gram units will cancel. We multiply by 100% to make it a percent, and there we have our mass percent concentration expression. Okay, so as an example, let's imagine we have a solution that we made by mixing 8.00 grams of potassium chloride, which is our solute, with 42.00 grams of water, which is our solvent. So in this example, to find the mass percent of KCl in that solution, we take our mass of solute, the potassium chloride, 8.00 grams, divided by the mass of the solution, which we don't have directly, but we are able to add the mass of the solute, 8.00 grams of KCl, plus the mass of the solvent, 42.00 grams of water, to get an overall solution mass of 50.00 grams. When we divide the 8.00 grams of KCl by the 50.00 grams of solution, and then multiply by 100% to make it a percentage, we find a mass percent of 16.0%. 3 sig figs for the KCl gives us our limiting number of sig figs. That's why we're 16.0%. We also tend to indicate it with m/m to indicate it's a mass of solute per mass of solution. So not too bad. Hopefully a nice straightforward example. Certainly if you run into trouble when you're trying other examples or homework questions on your own, don't hesitate to get in touch if you need some help. Now, mass percents are also convenient because it's fairly easy to add masses, right? You have to be careful with liquids on a balance. You don't want to spill them and you don't want to cause any damage to the balance, but you can go ahead and measure out your solvent and your solute on the electronic balance. Typically, if you're dealing with a solid solute, we measure that one first because it's easiest to take a little out or add a little more. And then once you have your desired amount of solute, you can go ahead and add enough solvent to get to your total solution mass. So we see a picture of that. Chemists, we tend to be in too big a hurry for that, so we tend to use volumes and molarity, but in other disciplines where things may be at extreme temperature, geology for instance, where you may be dealing with very hot or very cold temperatures, volume does change with temperature, but mass does not. So mass might be a more desirable type of solution concentration. And as we saw, it's fairly straightforward, hopefully one that you can wrap your mind around. So it doesn't really matter whether we're talking about mass percent or volume percent or molarity. Let's take a look at these solution concentration problems in sort of a general sense. So our general guide here is to look at the given and needed quantities, right? Then we write our concentration expression, and then we substitute in solute and solution quantities until we get the desired expression. So if it's mass percent, we're substituting in masses. If it's molarity, we'd substitute in moles and liters, as we'll come to see. But this guide is good for any of these solution concentration expressions as long as you keep these general principles in mind. All right, so let's see how you do now that we did that one mass percent problem together and we talked about our general guide to calculating these things. Let's take a learning check moment. So in this learning check, you're told a solution is prepared with 15.0 grams of sodium carbonate and 235 grams of water. What is the mass percent, mass per mass, just like we did before with the KCl example? This time we're looking for the mass percent of sodium carbonate in that solution. So go ahead, pause the video here, work it out on your own, and start us back up when you're ready to check your work. Good luck. Okay, so if you're following our guide, right, first step is to determine the quantities of solute and solution and analyze the problem. So here from the problem itself, we see that we have 15.0 grams of solute, that's sodium carbonate. We have an additional 235 grams of water, so therefore our solution mass is going to be the 15.0 grams of solute plus the 235 grams of solvent to give us an overall value of 250. We should really have a decimal point there because that 0 is significant. Our addition rule tells us that we add numbers in such a way that our result has the same place value of significance as our least significant, the ones place here for the water. So that's our problem. We know that we need that mass percent, the grams of sodium carbonate per 100 grams of solution, and it's obviously a mass per mass problem. Okay, so hopefully step 1 went well. Now we're on to step 2, where we write the concentration expression. Since we're dealing in this example with mass percent, our expression is mass percent equals mass of solute in grams divided by mass of solution in grams times 100% to make it a percentage. So on to step 3, we can substitute in our solute and solution quantities and calculate, and we find that 15.0 grams of Na2CO3 divided by 250 decimal point grams of solution times 100% equals 6.00% mass per mass of sodium carbonate in that solution. So hopefully that's the same one you arrived at. Maybe some sig fig issues, but hopefully not. Hopefully you've got the hang of those and you're ready for more. If not, if you do need some help, please, as I said, don't hesitate to reach out for help. Okay, so moving on now to volume percent. So volume percent, in this example, it's volume per volume. So the percent of volume of solute, so it'd have to be a liquid solute in most cases, in a solution, which would involve a liquid solution, we have a volume percent, V per V equals volume of solute divided by volume of solution times 100%. So just substituting in volumes for masses from our mass percent. So in this example, a 7% volume per volume solution contains 7 milliliters of solute per 100 milliliters of solution. So there we have our generic volume percent, volume per volume expression. Not as commonly used, but sometimes important, especially if we're dealing with liquid solutes and liquid solutions. Let's go ahead and follow up with a learning check here as well. So in this example, a bottle contains 59 milliliters of lemon extract solution. If the solution contains 49 milliliters of alcohol, what is the volume percent, V per V, of the alcohol in the extract solution? So notice we're looking at the alcohol here, and please go ahead and pause the video while you figure this one out. Should be very similar to the last learning check, only substituting milliliter volumes in where we were using gram masses before. Good luck. Okay, so step number 1, determine the quantities of solute and solution. In this case, the quantity of our solute is 49 milliliters of alcohol. We have 59 milliliters of extract solution, so we're looking for the overall volume per volume percent in this example. Okay, moving on to step 2, we're going to write that volume percent. Volume per volume is volume of solute divided by volume of solution times 100%. And so finally now on to step 3, we can substitute in our amounts. So 49 milliliters of alcohol and 59 milliliters of solution gives us, in this case, 83% volume per volume of alcohol. So it's really the majority component, so it's just one of the substances. We probably wouldn't want to necessarily call it solute. I guess it's one of the solutes, but ordinarily we think of solute as the thing present in the smaller amount. Here it's a larger amount for this alcohol in that extract solution. So we can do it either way, and just realize that either substance can be the solute when we're dealing with liquid solutions, just one's in a greater amount and one's in a lesser amount. So now we can combine the ideas of mass percent and volume percent into a single mass per volume percent. And this is important because it is very common for those of you headed into the health professions in intravenous solutions and medications. So we're looking at the grams of solute divided by the milliliters of solution. And then, of course, if it's a percentage, we need to multiply by 100%. So for instance, a 5% mass per volume solution contains 5 grams of solute per 100 milliliters of solution. So why on earth would we complicate things like this? Well, the reason for mass per volume percent solutions is the same reason that chemists use the molarity expression, and we'll see that in a few moments. But for now, it's very convenient to measure masses, as we saw in our mass per mass example. So if we're dealing with medications, for instance, or saline solution for patients, you can very easily measure out the solid, say sodium chloride for physiological saline solution, and then you add enough volume of solvent to get you to a specific amount. So we see these special volumetric flasks here have an etch mark at exactly 250 milliliters. So you can measure out the mass of the solid powder and then just add enough water to get up to that line, and you very conveniently made a solution. That's why we use mass per volume percent. You'll see chemists, we tend, instead of to use the mass in grams, we'll use the moles, which is just taking that mass in grams divided by the molar mass. So mass per volume percent solutions are quite common, especially in the health professions, so be on the lookout for those. If we see in this example 5.0 grams of potassium iodide were added, and then 250 milliliters of solution was made by simply adding enough water to go up to the mark. This gives us a 2.0% mass per volume percent solution of potassium iodide. Okay, now here we are, the chemist's unit for solution concentration, molarity, which is moles per liter. So this is the most common way to see a solution concentration expressed in a chemistry setting. And so that definition, molarity is equal mole of solute divided by liters of solution. So notice it's a big M, technically italicized, but that's not always followed. So if we have 2.0 moles of sodium chloride dissolved in enough water to prepare 1.0 liters of solution, the resulting NaCl solution has a molarity of 2.0 molar, is how we pronounce that big M unit. So we see we just took the moles, 2.0 moles of NaCl divided by 1.0 liters of solution, and we end up with 2.0 molar, big M, mole per liter NaCl solution. So not anything terribly different than what we've been doing, just being careful to keep track of the particular unit for this particular solution concentration expression. Okay, and looking just like at the mass per volume percent, we're taking our solid, which we don't have a balance that measures out moles. We'd have to actually figure out, it'd be roughly what, 60 moles per, 60 grams rather per mole of NaCl, so roughly 120 grams of NaCl is what would be measured. Be measured on a balance to the gram mass, but of course it would relate to a certain mole amount, in this case 2.0 moles, and then the solid would be added first using a funnel to make sure you get total transfer of solid, and then finally, just like we did before with the mass per volume percent, add enough volume of solvent to go up to a predefined mark on the volumetric glassware. So it's convenient, it's nice, easy to use. Chemists do most of our work around room temperature and pressure, so the volume difference isn't a big deal, but as I mentioned earlier, maybe a geologist would want a mass percent because they do have particular temperature fluctuations for where they do their work. Okay, so let's see how you do with a molarity problem. So in this case, you're asked what is the molarity of a 0.350 liter solution that contains 46 grams of KCl. So notice it's a gram mass, and this is not a mass per volume percent, this is a molarity. So you're going to have to convert that gram mass into moles before dividing by that 0.350 liters. So good luck. Pause the video here while you do that math and start us back up when you're ready to check your work. Okay, so hopefully you've caught on that we're going to use this guide no matter what particular solution concentration expression we're following. So step 1 is always the same, determine the quantities of solute and solution. So in this example we have 46 grams of KCl, we have 0.350 liters of KCl solution, and we're looking for the molarity, which is going to be the moles of KCl per liter of solution. So hopefully you were able to identify that. Now sometimes I might give you the volume in milliliters. For instance, I might have said 350 decimal point milliliters of solution. So there'd just be one more step of converting milliliters into liters, but it doesn't make it any harder than this one. Okay, so still in step 1 here, we actually have to find moles of KCl, right? We were given a gram mass. So in order to do that, we have to look at our trusty periodic table. We see that potassium is assigned a molar mass of 39.1 grams per mole. We see that chlorine is assigned a mass of 35.45, or we'll just round it up to 35.5. And when we sum those together, we end up with an overall value of 74.6 grams of KCl per mole. Now we could say 1 mole over 74.6 grams of KCl, but since they're equivalent, we could also say 74.6 grams of KCl over 1 mole. So we have to look and see which way is correct here. If we want to cancel the gram unit of KCl, because we're given the mass in grams, we need to have 1 mole of KCl in the numerator and the 74.6 grams of KCl in the denominator, and that gives us a value of 0.62 moles of KCl. So we've taken the mass we were given and we've converted it into a mole amount. Moving on to step 2, this is molarity. So our expression is molarity, big M, equals moles of solute per liters of solution. And now for step 3, since we did all the hard work in step 1, we can simply substitute in that mole value for the solute, 0.62 moles of KCl, divided by the solution volume, 0.350 liters. And as I mentioned, sometimes you'll see it in milliliters, but this time I was kind. And that equals an overall molarity of 1.8 molar KCl solution. So hopefully that's where you got. If not, if you made a misstep here or there, but now you understand, that's great. That's why we do these learning checks. If you're struggling, you don't know what's going on, please reach out to me for some help and I'll try to guide you along the way. And here we see in table 10, we have the summary of the types of concentration expressions and their units. So concentration, we're always dealing with solute and solution. For mass percent, the mass per mass variety, it's grams of solute over grams of solution. For volume per volume percent, we're dealing with volume, usually in milliliters of solute and milliliters of solution. For mass per volume percent, it's grams of solute divided by milliliters of solution. And then finally, for molarity, we have moles of solute divided by liters of solution. There's even more. There's molality that deals with mass per liters and all sorts of interesting things. Or molality, I'm sorry, is moles per kilogram mass. But these are plenty for now, and these are good enough to help you understand the different solution concentration expressions, and the ones that you'll tend to see, again, in chemistry will be molarity. In the health professions, maybe more mass per volume percent. Now, another reason we love these concentration values so much is that we can use them as conversion factors in our dimensional analysis setup. So the value of the 100 in the denominator of a percent expression is an exact number. It's not going to influence the number of sig figs. So if we have a 15% mass per mass KCl solution, like we see at the top of table 811, that means there's exactly 15 grams in 100 grams of KCl solution. So the 15 may have some sig figs associated with it. The 100 may have some sig figs associated with it, but when we talk about the percent, when we multiply by 100%, that 100 in the percentage is infinitely significant. Skipping down to molarity, we see 6.0 molar HCl solution has 6.0 moles of HCl in 1 liter of HCl solution. So we can have either the moles of HCl on top and the 1 liter in the denominator, or the 1 liter up top and the 6.0 moles in the denominator. But that 1 liter is exactly 1 liter. It's the 6.0 moles that will limit your sig figs. All right, so let's pause with another learning check and see how well you understand this idea of using solution concentration expressions as conversion factors. So for 1, 2, and 3 here, go ahead and represent those solution concentration values as 2 potential conversion factors for each solution. So pause the video here while you do that and start us back up when you're ready to check your work. Good luck. Okay, and so here we don't have a guide or anything fancy like that. It's just pretty straightforward, I hope. An 8.50 mass per mass percent NaOH solution means there's 8.50 grams of NaOH per 100 grams of solution, but that also means we can do the inverse and say 100 grams of solution has 8.50 grams of NaOH, and we could use it either way, whichever way is appropriate for a dimensional analysis problem. For number 2, we have a 4.8% mass per volume HCl solution. So here this means there's 4.8 grams of HCl in 100 milliliters of solution. It also means in 100 milliliters of solution there's 4.8 grams of HCl, so we can represent that either way. Finally, for our third part, we have 3.4 molar NaOH, which means we have 3.4 moles of NaOH per 1 liter of solution, but it also means we have 1 liter of solution per 3.4 moles of NaOH. So depending on the dimensional analysis setup, we may need to have it one way or the other so that it will correctly cancel and give us our desired result. So just feel comfortable representing them either way. I know it's more common that you would have the 3.4 moles per 1 liter for a 3.4 molar NaOH solution, but don't forget you can invert that. It's still the same thing, and maybe you'll need the inverse form for a dimensional analysis setup. Okay, so moving back to our guide now, we can have our guide to using concentration to calculate mass or volume. So first, as usual, we're going to state the given and needed quantities. Then we'll write a plan to calculate the mass or the volume, whatever's relevant based on the particular question. Finally, we'll write the equalities and the conversion factors, those items we just discussed, and we'll figure out how to represent them correctly to get them to cancel. And finally, we'll set up the problem to calculate the mass or the volume, whichever is requested in the given question. All right, so let's go ahead and practice this with a learning check. Okay, so in this particular learning check, you are asked how many grams of NaCl are needed to prepare 225 grams of a 10.0 mass per mass NaCl solution. So go ahead, apply our guide that we just discussed, and pause the video here while you work this problem. And when you're all set to check your work, start us back up. Hopefully we end at the same correct answer. Good luck. Okay, so here we are. Step one, we're going to state the given and needed quantities and analyze the problem. So we're given the 225 grams of NaCl solution. We're given that it's a 10.0 mass per mass percent NaCl solution. The thing we need is the number of grams of NaCl. So we've analyzed the problem here. We're ready to move on to the next step. Okay, so in step two, we're writing our plan to calculate mass or volume. In this case, we need mass. So we're going to take the grams of solution and we're going to use that mass per mass percent as our conversion factor to figure out the grams of NaCl. So that's our plan. Hopefully that's the plan you used, and let's see how we specifically enact that plan. All right, moving on to step three, we can write our equalities and our conversion factors. So because this is a 10.0% mass per mass percent NaCl solution, that means that 10.0 grams of NaCl equals 100 grams of NaCl solution. So we can either have the 10.0 grams of NaCl up top and the 100 grams rather of NaCl solution in the denominator, or we could have the 100 grams of NaCl solution as the numerator and the 10.0 grams of NaCl as our denominator. Step 4 is going to show us that in this particular case, we want the 10.0 grams of NaCl in the numerator because we need to cancel the unit of grams of NaCl solution. So in step 4, we take that 225 grams of NaCl solution, we multiply by 10.0 grams of NaCl per 100 grams of NaCl solution to cancel out grams of NaCl solution, and we end up with 22.5 grams of NaCl. Be careful that you remember to divide by 100 there. Just cancel the units, don't cancel that number. That's why we end up with obviously less NaCl than of NaCl solution. Hopefully that was what you got, and if it's not, hopefully now you understand how to do the problem correctly. If you are lost and you try the homework and additional practice problems and it's just not helping, please don't frustrate yourself. Get in touch with me. I'll try to do my best to guide you the right way. Okay, let's try another learning check. Make sure that either you really do understand it or give you another chance to get it. This time we're asked how many liters of a 2.00 molar NaCl solution are needed to provide 67.3 grams of NaCl. So go ahead and pause the video here. Make sure that you are looking at your potential conversion factors, using that concentration as a conversion factor to arrive at the correct answer. Once you think you've gotten there, go ahead, start back up. We'll check our work and hopefully we end up at the same correct place. Okay, step 1, state the given and needed quantities, analyze the problem. Here we're given 67.3 grams of NaCl. We're given that it's a 2.00 molar NaCl solution. What we need to know is the number of liters of NaCl solution. So that's step 1. Hopefully that was pretty easy and straightforward for you. All right, moving on to step 2. Now our plan this time involves a couple of steps, right? Because first we start with the grams of NaCl, but we're going to need to get to moles of NaCl because we're dealing with molarity, which is moles per liter. So we're going to need to use molar mass as a conversion factor first to go from grams of NaCl to moles of NaCl. Then we can use molarity as a conversion factor to go from moles of NaCl to liters of NaCl. So it is a little more complex than our previous examples, and of course it's the one that the chemists love to use, right? So hopefully you get the hang of it quickly, and hopefully you were able to do that correctly on your own. All right, so moving on to step 3, we'll write our equalities and conversion factors. So we know that 1 mole of NaCl equals 58.5 grams of NaCl from the periodic table. Just adding the masses of sodium and chlorine from the table, we get that value at least to 1 decimal place. That means we can either say 1 mole NaCl divided by 58.5 grams of NaCl, or we can do the inverse, 58.5 grams of NaCl over 1 mole of NaCl. We can also represent our molarity in 2 different ways, right? Our molarity tells us that 2.00 moles of NaCl equals 1 liter of NaCl solution for this case. So we can have the 2.00 moles of NaCl up top and the 1 liter of NaCl solution in the denominator. or we can have the 1 liter of NaCl solution in the numerator and 2.00 moles of NaCl in the denominator. When we move on to step 4, that will show us the correct way to represent our conversion factors for both molar mass and for solution concentration. Okay, so finally here we are with step 4, set up the problem to calculate the mass or the volume. In this case, we're looking for volume. And so we take our 67.3 grams of NaCl, we multiply that by 1 mole of NaCl over 58.5 grams of NaCl, because obviously that's going to let us cancel grams of NaCl, so that's the correct form. Then we need to multiply it by the form of the molarity that will let us cancel moles of NaCl. So that actually requires us to put the 1 liter of NaCl solution in the numerator and the 2.00 mole NaCl in the denominator. Now we're in liters of NaCl, just like we want to be, and when we do the math correctly, we end up with 0.575 liters of NaCl solution. So there we have it. Hopefully where you arrived on your own. If not, hopefully now you understand how to get there, and you could do so on a practice problem or an exam problem or whatever the case may be. If that's not true, if you're struggling, you're not sure what's going on, this hasn't been helpful for you, please do reach out so that we don't get you any more frustrated and we get you to the place you need to be to do well on the questions for the homework and the test, and just to get the knowledge that you need from the course. Hopefully you are doing well and understanding it, and we'll see you in the next section.